All right, ladies and gentlemen, so welcome back. So up to this point, we've been talking about the basic theory of how evolution works, um, but it is a theory, and so by definition, a scientific theory needs to have copious amounts, large amounts of evidence that end up supporting it. So that's what we're going to take a look at starting today, is what evidence do we have to support this idea that species change over time? And that evidence for evolution can get drawn from quite a variety of sources, which is why it's so highly supported. And we're going to talk about just a handful of types of data that exist to support this idea. So we'll start with the idea of the fossil record, a little bit about radiometric dating, some genetic information. We can talk about the distribution of where organisms live across the globe, and then also talk about some anatomical and developmental similarities that exist across organisms. So anatomy, remember, is just their body shape, their body plan, where their bones are, their muscles, and then how those sorts of structures develop over time. So let's start with the fossil record, and this is one of our most concrete, if you will, pieces of evidence that evolution exists. So when we talk about the fossil record, this is an archive or a history of evolution on Earth. And remember that a fossil is any sort of preserved or mineralized remains of an organism. So most of you have probably seen bones of dinosaurs and things like that. Or they can also be imprints. So a leaf that fell into mud and now you see the leaf print that is left behind. And although this record isn't complete for the past 3.5 billion years that Earth has existed, a lot of our modern knowledge about life on Earth as a whole does come from the fossil record. Now, like I said, it isn't complete. In order for a species to have been fossilized, there's a couple of pieces that would have had to fall into place. First off, that organism would have needed to die near water. So our fossils are only formed in sedimentary rock. And if you remember back to middle school, sedimentary rock happens when you get these sediments or these really little tiny particles of dirt and stone and rock that are floating around in flowing water. Okay, and that water eventually slows down enough that that sediment literally falls out of solution. So rather than it just being churned up in the water, water slows down, all that stuff settles to the bottom. Okay, and as those layers of sediment continue to build on top of each other, more and more pressure gets created, and eventually that sediment turns to stone or turns to rock. So in order for a organism to become fossilized, they have to die near water so that they can end up being covered up by that sediment so that they can then be pressurized and eventually turned to stone. Now, not only do they need to be where water is abundant and flowing enough to have that sediment exist in the first place, but that organism also has to get buried quick enough before it completely decays, or even more likely that it just gets scattered, its body gets scattered by scavengers. So when we talk scavengers in modern history, we're talking about birds of prey, vultures, eagles, that kind of stuff who will come in, they'll eat out the meat, but they may carry away bones as they go. So if I look at a fossil, maybe I find an individual bone, but that doesn't necessarily tell me much about the entire organism. So when we're looking at these big dinosaur skeletons, the fact that we are able to even find those is pretty crazy. And the fact that they even existed in the first place is pretty impressive because they would have needed to die near water and they would have needed to be covered up by the sediment in that water in a relatively quick enough period of time to keep them all together. So what we do have, though, is actually a pretty decent array of fossils when we look at this globally. So we look at the fossil record, and what that means is this order of how fossils appear within the layers of that sedimentary rock. So remember that every layer is like building a cake. So one layer has to get built on top of the other. And so the sediment, those layers, the deeper I go, the further back in time that I go. So each strata or each layer of rock forms on top of the one that was previously put down. So if I look, so long as those rock layers have remained undisturbed over time, I know the layers at the top are younger than the layers that are down bottom. And so I can use that as a general idea of how old something is, at least relative to the layers that are above and below it. So studying those fossils in those layers or in those strata over time enables us to trace evolution. I can see changes in species over time by the different types of body plans, different arrangements of bones that I see from one layer to the next. So those different strata have different fossils, all right? And not only are those different fossils in the sense of maybe they're small changes over time, right? Gradual change over time, something more like what you see down here. But we also see sudden changes or huge distinct changes from one layer to the next. When we talk about the dinosaurs, they exist up to a certain point and then they're just gone. The species went extinct. All right, the whole lot of them disappeared. And so we can see both these sudden changes as well as these smaller, more gradual changes over time that lead to big change when we look at it and step back from a overall big Earth history standpoint. So what can we understand or what can we infer from the distribution of fossils that we find? Well, first off, we know the deeper that we go that there are different organisms that used to live here on Earth that clearly no longer exist, right? And dinosaurs are the best example that most kids know. Also, we understand that today's organisms may look similar to things that existed in the fossil record, but there are clearly distinct, unique differences. If we look at something like a sloth, well, there used to be giant sloths. They no longer exist in that size and that form, but a smaller version seems to have continued to persist. So we understand that some sort of change has happened to that species over time. Also, if I look at fossils from one layer to the next, either above or below them, I may be able to see some smaller changes over time, and I can potentially infer what might have led to some of those changes. We also can just take a look at where those fossils exist. Some of them are concentrated in Europe, in Asia, in Africa, Australia, and some of them are found globally. So that tells us something about where these organisms used to exist on Earth compared to where our current continents exist. So if you can think back to middle school, remember talking continental drift, right? And that all of these continents used to exist in one big supercontinent called Pangaea. So things like dinosaurs and things could have gotten to all of those different locations. But as those continents began to shift apart from each other, the ability for those organisms to get from one landmass to the other decreased, and the environmental differences that existed on those continents changed over time, which forced the evolution of the species that continued to live there. So these are just some additional examples, things maybe that you didn't really think about. Here are hominid skulls. Hominids are basically human ancestors, so not quite human, but not quite ape, somewhere in between. So that's sort of our divergence from the great apes. Petrified trees. All right, fossilized trees. These are really cool because what they allow us to do is see the rings of the trees just like we do in a living tree, and that can tell us a lot about growth, so water and nutrients and things like that that would have existed at that particular time that that particular ring got formed. Now we can see that in a fossilized form, which is pretty cool. Ammonite casts, go hiking out in the woods and you'll see these guys. Same with the fossilized organic matter. So we see a lot of these types of fossils in the rocks around here. They're not necessarily fossils in the sense of like a bone of something, but they're imprints. All right, and those ammonite casts are really kind of cool because if you really pay attention to some of the fossils that exist around here, they're actually aquatic organisms. This particular landmass used to be essentially the seashore or under the ocean when we go back millions of years, which is pretty crazy to think about. And then these are fossils by definition in terms of a preserved piece of living matter, but they're not necessarily what most kids would think about. So a scorpion in amber. That's really pretty awesome in terms of a fossilized piece of material because you also now get some of the softer pieces that you wouldn't typically get in a traditional fossil, because you're preserving the entire organism as opposed to just sort of those harder bits, like bone and teeth and things like that. You'll get a lot more to get preserved when it gets stuck in that amber. Amber is just tree sap, that hardens over time. And so if an insect in particular, they're the ones who often get stuck in that kind of stuff. You're getting all of their exoskeleton and potentially even some blood and things like that, which is pretty crazy and cool. Iceman, all right, also a pretty unique set of circumstances because he is, well, preserved in ice. And once again, you get some more of that fleshier material that you wouldn't typically get from a traditional fossil. Okay, so sort of tying into this idea of distribution of species, whether they're fossilized or even the ones that we currently have in existence, there's an entire study of where organisms exist around the globe, and that's this idea of biogeography. So literally the geography of the Earth, layered on top of that with life. And so we see some really cool, interesting distributions of species. One that's kind of interesting is this idea that marsupials, they live in Australia. So those marsupials are organisms with a pouch. So kangaroos, for example. And what a lot of this biogeography does is really support the connection between the theory of continental drift and evolution. And so here's what I was talking about a moment ago, right? That idea of Pangea, where all of these continents that we now look at today used to be all connected, this one big supercontinent, right? And so continental drift, over time, we've got these plates that these continents sit on top of a liquid mantle. And so that all sort of floats on top of that. And you can see that the Atlantic Ocean is getting slightly larger every year. Pacific Ocean is actually getting a little bit smaller every year. And so all of this is slamming into each other, floating apart. You get a lot of crazy geologic activity along those fault lines. If you know anything about California, right, they get a lot of the earthquakes. Places like here, the India plate smashed into what is essentially Eurasia, all right, Asia and Russia and China and all that kind of good stuff. And so these get really high mountains. That's where your Himalayan mountains exist. Okay, a lot of volcanic eruptions, all kinds of good stuff. Okay, and that constantly is changing the landscape of these continents, which by association means that the organisms that live there adapt or die. Okay. The other cool thing about this that comes back to that support not only for evolution and those changes in environment that change the features of a species, but ties back to the continental drift idea, is something like these lungfish. All right, so these guys exist here in South America. They also exist in Africa. We get a little bit here in Australia as well. Take a look at all the fossilized distribution of organisms as well. And we can see they have a pretty global distribution between what currently is still alive and what is fossilized. And the only reason or the only way that that sort of distribution would have existed is if all of this was connected at one point. If Pangea did in fact exist, which we are pretty confident at this point that is the case. But when we see some of the differences in the living lungfish in these different continents, all right, that's a result of the fact that those populations of fish are no longer able to interact. There's no gene flow going on. They're not able to migrate from one continent to the other. They're separated by an ocean. And so some of the local environment has changed for them. And so we have seen the change in species, different species of these lungfish now existing in these different continents because of that continental drift.